Yeah. Now, Subhasis, I think.
Okay, so thanks, Bhaktosh, for this nice introduction. So it is not just about the new paper what we have wrote, but this is just the type of work I was doing in last couple of years. But I will not show the previous works, but it's basically on the recent work, mainly focusing on this quantum scars. So many word quantum scar, etc. This has become quite an interesting topic these days. And you can see also this left panel, this picture, this actually shows this quantum butterfly effect, which has also recently become very interesting topic after this black hole thermalization concept of black hole thermalization and Sajdev A. Kitev model. And I think very recently there is also another paper came that they're showing there is no such quantum butterfly effect in certain cases. So this is still a very interesting I think topic. There are various new things that has been developed, also the how to understand the chaotic behavior in the many body system, quantum many body system as well. It has also the importance in the quantum information theory, etc. So, well, so the plan of the talk is the following. So first I'll just give a brief introduction on this non-equilibrium many-body dynamics and thermalization, etc., ergodic properties. And then I'll just briefly discuss the two models. One is a coupled top model, and next one is the Bose-Josephson junction coupled to the bosonic bath, and next summary, etc. So the non-equilibrium dynamics in the quantum many-body system has become a very interesting topic, particularly in the ultra-cold atomic system. Now they can also, there's a tunability of the various parameters, and as well they can also dynamically change the parameters like interaction strength, the lattice hopping, various things that can be tuned with a time-dependent fashion. So also that there is a imaging technique, the real space imaging is possible, unlike in the solid state cases. So where there's a meaning people can study the how this interacting quantum many body system behaves under such type of tuning, or if you want to change the parameters so that the system can go from one phase to another phase, or there is a some type of a, it's called the quench dynamics across the, what is the behavior of the quench dynamics, etc. So also the related question that is interesting is that whether the system shows the thermalization. A closed system, when the closed interacting many body system with lot of degrees of freedom shows the thermalization under this quench or this change of the abrupt change of the parameters, etc. When this thing happens. In fact, when we teach the statistical mechanics, this is something very unpleasant question that we try to just put it under the carpet and try to just rely on Gibbs and just say that there is a equivalence between this time average and ensemble average, etc., and go to the microcanonical ensemble. Even microcanonical ensemble is also a bit uneasy. I always get some sort of uneasy feeling when discussing about the microcanonical ensemble. There is no guarantee that a simple system like harmonic oscillator or etc. that will be describable by the microcanonical ensemble or not, that nobody knows. In fact, that is a big question. When it comes to the canonical ensemble, grand canonical ensemble, systems are okay. It is, one can describe the thermodynamics in a proper way, because this is like a connection with a heat bath or etc. It will just thermalize in connection with a heat bath. These types of concepts are there. But when an isolated quantum system is just considered, then under what condition they will thermalize, or what condition the whole phase space will be covered, that is the ergodic hypothesis will be satisfied, that question is still really an unsolved thing. So at least in the classical sense, we have some expectation that if there is a chaotic behavior and there's a lot of large degrees of freedom, lot of collision, or even the these types of boundary effect, this pictures, it shows the irregular boundary, it shows the chaotic and ergodic motion, and that leads to the phase space mixing and the thermalization of the system. Whereas in the quantum system, there is no such underlying connection between chaos. However, we have studied that there is few cases one can try to connect. There is a underlying classical behavior that can trigger this thermalization in the quantum system. But for quantum system, there's a eigenstate thermalization hypothesis, which is called the ETH, that has been proposed by Deutsch and Srednicki. So the idea is they have just shown that the thermalization that occurs at the level of each eigenstate, depending on their energy density, there will be thermalization or the expectation value of the observable that will correspond to the microcanonical ensemble. Or in other words, one can get a diagonal kind of density matrix in this system. So this has a close resemblance with the random matrix theory. When the eigenstates become almost like random, they correspond to this like thermalization hypothesis. And this has a so there is a belief that the quantum chaos and ergodicity, this is responsible for this eigenstate thermalization hypothesis, and this ergodicity of the quantum system is also closely related to the random matrix theory. So random matrix theory turns out to be a very important and useful tool to understand many of these complex phenomena of the quantum many-body system in a Hamiltonian independent manner, trying to understand it from the not from the just typical Hamiltonian thing, but from the spectral property to understand the system's behavior under non-equilibrium dynamics. So, but there is of course various systems that turns out that they do not follow this eigenstate thermalization hypothesis also. And I will basically discuss about this thing, which system, what are the main cause or main factors that for violation of ETH thing. So factors hindering the thermalization are the following. It's believed, this is a common expectation. So first thing is the integrable model. So it is believed that if there are a lot of system is integrable, then there are a lot of conserved quantities will be there, and so the system will not be chaotic. That will hinder this phase space mixing, and ETH violation will be there. But still there is a lot of question, meaning there are certain systems like XXX model, meaning spin system, etc., where people still see some sort of ETH is still valid in the weak sense, not very strongly, but still there is some thermalization. Even if there is a reasonable number of integrable quantity, then there is a new concept that is called the system can thermalize, and thermalize to something called the generalized Gibbs ensemble, depending on the other integrals of motion. So there are various possibilities, and this is still questionable thing, but it is a common belief that we generally start with a non-integrable model, non-integrable regime, so the system can be thermalized very fast, and the ETH can be tested for such systems. And there is another kind of systems are there which are called this many-body localized, or the many-body localized or many-body localization phenomena, which demonstrate. So these are meaning it's like somewhat similar to Anderson localization. In presence of disorder, we see that we know that in one dimension that all the states getting the localized, they are not extended state, they are localized. But this is just the ground state property typically. But the many body localization, not only the ground state, also the higher energy states, they are also getting localized. There is a typical behavior of the entanglement, entropy growth, all this kind of behavior. So basically it doesn't thermalize at all. So these systems remain localized at some point. So if we just create some, in the experiment, people have done these things in the Munich, I think, yeah, I think it is the Munich group. They have done this experiment. They started with some charge density wave type of phase, and they found out that phase remains there. So it does not decay for this thing. So system is many body localized in that sense. And there are also some other system when this is not completely many body localized, the states are completely localized. So there is no such extended, meaning is completely localized. There is no such system dependence of this, system size dependence in that case. But there are certain states are there, certain systems where the states are in between the localized and extended nature. So these are called these non-ergodic states. So typically the many body localized states, when they have the in presence of some interaction, repulsive interaction, etc., they typically show the type of behavior, this non-ergodic behavior, and there are the presence of this non-ergodic states are there. This is called the multifractal. So they also they thermalize in an anomalous way. There can be the anomalous thermalization or anomalous diffusion. These types of phenomena can be observed, and they typically violate all these states. They violate this ETH thing hypothesis. So one this diagonal ensemble type of picture or the microcanonical behavior, this is not observable in those types of states. Nevertheless, they are not completely localized, but there is certain anomalous behavior can be observed. And very recently this thing has been observed. There's a many body quantum scar. So there are certain states there in the system that does not thermalize. So I'll just discuss this particular thing in this talk. This is the main focus of the present talk, that today's talk, that is many body quantum scars and how these many body quantum scars are forming. But first I'll just talk about a little bit about this non-ergodic state. This has also become very interesting topic in present days to understanding the anomalous thermalization behavior. So last year we have done some work on these things. So in the
Subhasis, Soren
yes,
here. Just a question in the previous slide. So if we
yeah,
compare, can you hear me?
yeah,
Subhasis?
I can, yeah,
Yeah. So if we compare localization, general Anderson localized things versus many body localized, will the Anderson localized material, like let's say electrons in disorder, they follow thermalization hypothesis, or they also don't follow? And many body localizes, of course,
no,
especially
of
Fox
course,
space
no, no,
localization.
of course,
Yeah.
they do not follow these
Yeah.
certain states. When this is the states which are localized, of course, they will not follow the thermalization hypothesis. But
Right.
the point is, there can be still there is a possibility of the extended state. It is just the ground state property, but many body localization is not just the ground state property of this.
It's an infinite temperature statement in a sense. That's what you're saying, right? Is that
Well,
what
I
you're
mean,
trying
it
to say?
just goes to the correspond to the microcanonical ensemble corresponding to the energy density of this state. So it is the microcanonical ensemble corresponding to the energy. Yeah.
Hmm. Okay.
Shubhashish, another small question.
Yeah.
We know that the many body localized phases have some integrals of motion in them, so-called
Exactly.
local integrals
Yeah.
of motion.
Yeah.
So
Yeah.
in some
Right.
sense, that shares a commonality with the integrable models you were talking about.
To
Some
some extent,
commonality,
yes.
to some
Exactly.
extent,
Exactly.
right?
Exactly.
Even though
Exactly.
they're more
Exactly.
glassy phases of nature.
Yeah. Yeah. Exactly.
Right.
Yeah.
But
Yeah.
my question was, what about these non-ergodic states? Do they show
So
any integrals of motion?
non-ergodic states are to some extent are related to the basically somewhat like the glassy behavior. Of course, they have this anomalous kind of thing. So it's a nature of states. They are not. There's some sense are multifractal. That is the main
And
thing.
are there any known integrals of motion for these non-ergodic states? Do you know of any examples?
There is a integral of motion.
Are there any? I mean, or does the multifractal nature not allow for that?
Yeah, say actually this can happen in this way. So let's say if you consider a start with a many body localized state, then you have a lot of integral of motion, local
Right.
integral of motion.
Right.
Then you try to make these things some impure, meaning in some sense you put some repulsive interaction, strong repulsive interaction. Then you may find in the within certain energy density. I think this is a recent work of Subroto. Subroto has presented in the QMAT meeting this work. I think this is a very interesting thing. So what he has found out in the certain energy density, that system becomes localized, and then within above that, within certain regime, this is like this non-ergodic states evolve. Okay, so these types of behavior is an energy dependent behavior
Right.
of
Right.
this
Right.
this phenomena.
Okay.
Yeah, this is some sense this happens, meaning is
So
not
what is
exactly
to
the
define
number of
ergodicity for quantum states? Sorry.
Sorry.
So how do you
Hello?
define ergodicity for quantum states for a quantum system? So what is the definition?
Well, there are various ways to define the ergodic behavior. That is the. I will come to this point later. Maybe there are various ways people can try to
Sure.
see. Okay.
But,
So
Subhasis,
when we are at
later.
question, can I also ask one, Amit here?
Yeah, sure. Yeah,
so this so for example, let's take this intermediate one, this non-ergodic but extended state, the one that we are talking about.
Yeah.
So now in that, if I, let's say, switch off the quantum fluctuations, I make the quantum fluctuation tending to zero, will it go to a classical glassy state?
Will it go to the classical glassy state? Actually,
Glass. I mean,
frankly,
I'm thinking glassy being a classical state. I mean, people talk about quantum glasses, but I think that's far less weaker. That is on a
yeah.
weaker footing yet. So let's talk. I mean, so basically, I want to get rid of the quantum fluctuation. Then does this non-ergodic, this but extended state, the intermediate one, will lead to
I
a glassy?
Well, I guess in some sense one can say that similarity, like in terms of maybe one can see in terms of the anomalous diffusion or these types of behavior, there is some similarity one can find, but the basic mechanism maybe is different, because for glassy thing there is a lot of the local minima that basically matters. So there is some sort of a local minimas that is in the energy landscape that's playing the main crucial role. Here, perhaps the nature of the states, the quantum states, that is become the playing the important role. So there is no direct, I think, one-to-one analog of this. These states correspond to some type of local minima of some given free energy. That I cannot say. I think is a one needs to check. There is a difference. Certainly, there is certain difference. Probably.
Subhasis, Chiranjeev here. So just a follow-up
Okay, thank you.
question is that in glassy phenomena, you still have some relaxation. Maybe it's a very long-lived like relaxation.
Yeah, exactly.
Here
Yeah.
there are no relaxation, right? So it will be frozen, completely frozen, right? In many mode localization. Hello?
No, but here one is talking about this non-ergodic but extended state, the one which is intermediate.
I think Subhasis'
Full
connection is
many-body
lost.
localized state.
Wait, Amit, Subhasis' connection is lost.
Okay, my connection was little bit.
Yeah,
I
I
think was
understood.
disconnected.
Did you hear the question which I said?
No. I did. I was just
Okay. So
at the first line. Yeah.
In glassy system, you still have some relaxation. It's a very long.
Yes. Yeah.
But here it is completely frozen, right? In these cases, in the many-body localization.
Yeah, this is actually an interesting question. The question you said, there is a still debate going on in certain cases. So typically in the many-body localization, people try to build up the many-body localized state from the Anderson localization with the impurity, then putting some interaction, many-body, etc., and then try to build up. Now the question is, many-body localization is first introduced by David Hughes. So it is some type of a state which does not really require the disorder. Disorder is not the key ingredient for the many-body localization. So according to the definition, so there is a still search for certain system which can give a long-lived excited states or something like that. So recently there is certain systems like a dipolar gas with a dipolar fermions, and it turns out that double states or like doubly occupied states, etc., if one prepares certain states, it turns out a very long-lived, although it is not like infinitely, meaning it is not exactly like the many-body localization. There is a relaxation, but very slow relaxation. So there is a still type of questionable point. So also, meaning this is a very interesting question, whether one can realize such many-body localized system just purely from the interaction. This is a without disorder, but purely interaction. There can be long-lived. I mean, relaxation can be very long. Yeah.
So, actually, one application of this would be very good for because the entanglement is very robust in this case, right? So that it is not prone to decoherence. So, like, right?
So yes, a volume law. Yeah, it's a.
These would be very useful states. Take it. Fine.
Okay. But Subhasis, just to follow Amit's question, so if we think that if you introduce quantum decoherence, I think if we have to say that will it go from quantum to classical, if I introduce decoherence, do you think it will become a classical glass? glassy state, right? That's probably one way to look at it, right?
This is also I don't
That's
know
not clear.
exactly whether
That's
this
not
will be
clear.
same, meaning whether this will be same behavior or not, because glass has a different origin, different thing. So, but in this case, of course, you can do. Meaning this is also a interesting aspect. People are looking into this. What is the fate of the many body localized system in presence of dissipation? Okay,
Right.
so most likely it may, meaning the many body localized localization phenomena may be gone in some sense, or if the, it perhaps it will depend on the dissipation strength of this decoherence or all this. So this
And so,
depends.
Subhasis, the other thing is that
Yeah.
I think the reference to, I think the first work really was in the context of a quantum dot. You remember this was Alailer, Alschuler, Geffen, and somebody else. 4 people. They introduced this many body localization in a quantum dot, where they saw the Fox space localization. That was long back before I think these people came up
It
with the
is
idea. That was the original idea.
Artschuler, Aligner, they're actually doing these things. Yeah,
They
that's
were the
true. But
first one to actually
this,
point out this
but I
kind of.
don't know. This is nowadays. This is when people say, meaning if you, I don't want to go into that discussion. That well,
It's just that
I think
that is where they
this
saw it
David
first
Hughes's
time.
concept probably, but
The
yeah.
first time saw it in that context, that they saw that Fox space is localized. Right?
No,
And
that
that's
is
what the,
that is okay. That can be there, but the way David Hughes has proposed this idea, this doesn't really require this any
right, disorder. I think they
type
got
of
rid of the
disorder.
disorder part of
Exactly,
it.
that
Yeah,
was the
yeah,
thing, and
yeah.
he put
Yeah.
very strong condition on this growth of this entanglement, entropy, etc. All these properties.
Right.
So,
Okay.
glass and this classical glass versus this, I think one of the differences is that in the classical glass, the energy, as you say, that the energy landscape is localized. Here, the probability, the localization happens in the probability space, right? I mean, the wave function or the probability of the system being in certain space is localized.
Exactly.
So this is the
It is
difference.
basically in the, there is a difference. There is definitely a difference. But the point is, if you look at the dynamical sense, like the anomalous, the diffusion properties and all these things, or relaxation,
Or
etc.
long-term relaxation,
Maybe,
that also will be, there will
maybe
be
there
same,
is some
similar.
sort of similarity one can see very vaguely. One can make this similarity. But if one try to find out the origin of these types of behavior, so this is a glassy thing, is a purely the classical phenomena and all this. So of course, and now point is Amit's point is valid in that sense. Like now people are looking into many body localization of this say long range dipolar system, etc. Not in presence of disorder, but just presence of the interaction whether certain states can be look. It is a some type of a, people are still confused. I must say people are community is confused. This is just a evolving field, I must say. So it is not really meaning there is a some debate going on that whether one can call these things as a many body localization or it is like a long relaxation, some glassy behavior. Well, there is certain debate.
Anyway, I think one of the things which I find very confusing is the definitions are not ever properly stated. I mean, of course, we had a long discussion and we can discuss it afterwards. But like many of these things, because should mean something very specific. Things like even ergodicity, right? And I always get confused.
Yes.
Maybe we can discuss that later. I think already the discussion has gone on for too long.
Okay.
So Subhas's last comment, sorry for this. So can we say that at least in context of fermions, Fox space localization is a true many body localization? Can I make this statement or this is wrong? Is this exact?
Fox space localization is this is in fact as Siddharth is talking about this thing, this number of local integrals of motion. So now there is some type of model for model Hamiltonian has been proposed for this many body localized system, which turns out to be just a number operator. You can write down the local number operator, all these things, or SZ, etc. In the spin language, just writing down in the SZ or pseudo spin language, tau Z, etc. So
that's a reasonable marker. You think that's a reasonable marker?
Okay. Yeah. So typically in the localization phenomena, what we understand is a real space, meaning that's the mental picture we have. That way. But there are certain systems, like if you see this under that the model I'm showing here, this is if you forget about the long range hopping part, then this quasi-periodic disorder, this is called the Under model, and it has a very interesting property. It has a duality. So it is a one dimension. It undergoes the localization transition, and if you look at in the momentum space, it happens in the other way around.
Yeah, I mean,
So
in a
when it
sense,
is
the people
localized, it
could
is
kind of, I remember people could map the Fox space localization on the Calais standard localization, Anderson localization, right? When you take the Fox space and then you look at the events in the Fox space, then you can kind of map this to a
Sorin
Calais. Yeah,
Sorin, I can tell
yeah,
you one thing: these fields are evolving. So there is no
yeah.
such. First of all, in physics, it's very difficult to give any hard and fast definition of certain
I
things.
see. So
So
this
maybe
is
we can
There are
have
open.
some
certain
of
Very
this.
good.
phenomena
Like,
are like these things. So it is.
Right. Okay.
It is. I think it is hard to say that whether the Fox space localization is the localization of phenomena or etc.
Okay.
So
Fair
it
enough.
is typically this is our mental picture. This is the thing that we intuitively feel. That is that from Anderson localization we feel that's what happened. But I am also telling you there are examples where it shows the localization in real space, and when it is delocalized in real space, in momentum space, it got certain localization behavior is there. So there are certain ways, or you can see the this way, the doublon localization. There are certain
Right. Yeah.
parts, certain collective variables. There is a localization, or certain degrees of freedom. One has to find out which are localized. So, well, that is true. It is our general common sense. This is the real space. We always consider the real space localization is the localization in that sense.
Okay. Thanks. Yeah.
Okay. So yeah, so this just last year we have done some work on the non-ergodic to ergodic transition. So this is a model with a one-dimensional model with a quasi-periodic disorder, and this quasi-periodic potential is called the Andre-Aubry model, and this potential shows a very interesting property. One dimension, it shows the localization, delocalization, localization transition, which is general Anderson localization, random impurity. It is the 3-dimension it occurs. So it's a 1-dimension, the same phenomena can be seen. And this has been also observed in the localization of light as well as localization of Bose-Einstein condensate, etc. But we consider there is a long range hopping, and the hopping term, there is a power law. It's a is there. So I minus j whole to the power a. This term is important for the extended Andre-Aubry. What we found that if this a is larger, then it will be like a usual localization to delocalization. Of course, there will be the mobility age will be there. And various band like states will be just get localized one after another as we increase the strength of this quasi-periodic disorder. But interesting part is if the a is less than 1, meaning really a long range hopping, then it turns out there can be a ergodic to non-ergodic type of states will be formed. So these states like P2, P3, etc., these are like the different bands of the non-ergodic states, and these are not really neither they are completely extended nor they are localized. So these are like the multifractal type of states are there, and it also shows that there is a multifractal dimension, fractal dimension like D2, that shows a very interesting behavior as we change the strength of this quasi-periodic disorder. So there's a various interesting in this quasi-periodic system. One can see this. This work is done with my student Shayok, and there's a Russian group. Not Russian. There's a Paris group actually. Slapnikov is Russian, but he's in Paris, and this Hanover group, Luis Santos, is also there. So next also we have seen, so this is like the long range hopping term gives these types of transition, this non-ergodic to ergodic like transition.
This value of A,
Yeah.
so is there any constraint in terms of the boundedness of the energy with the system size or the energy density with the system size? If A is meaning A,
no, you can scale it appropriately.
value,
Here
right?
there is no problem. Here there is no problem, but
Okay.
it is. So and there's another work also we did with a quasi-periodic driven spin and with Shayok and Diptiman. So this is a very interesting system. If we have a quasi-periodically drive a spin, then it turns out the classical dynamics, it's a very interesting behavior, like it just covers up the whole block sphere. So the dynamics looks like almost chaotic, but actually the Lyapunov exponent is 0. There is a vanishing Lyapunov exponent, and it's a very, very irregular motion. But if one tries to analyze the classical dynamics in the Fourier space, etc., one can reveal there is a fractality, fractal behavior is there. And also in the quantum evolution, we have, if we just find out the equivalent of this Fluke operator and the time evolution, then it turns out that there is a very meaning fractal behavior also there in the quantum level. And it turns out that if we have two interacting spin, two spin instead of a one spin, if we just have two spin and the interaction between them, then with a tuning the interaction strength, this non-ergodic or fractal behavior just changes and the system immediately thermalizes, and it will just show these types of diagonal density matrix in the quantum system. So there are various ways one can see these types of ergodic to non-ergodic transition, also with an interacting system in presence of disorder and interaction.
The size of the spin matters here. The size of the spin. Oh, that's
size
irrelevant.
of the spin we have taken, it's a, of course it is not a half. If we take a
Yes,
half, I mean, that's a no, but half actually there's a controversy actually started with the spin half. This was the famous paper of is an experiment also done, and this is a very famous paper of this guy, this French guy. I forgot this in I mean, these days I cannot remember the names, but anyway. So so this was the idea is that if there is some magnetic field which is just flipping in the some type of irregular sequences, then whether the dynamics will show this type of irregular or this chaos is there, etc. And in fact, there are people like Henry Orland, even Kadanov, they were also involved. There are very interesting papers in the Journal of Statistical Physics. So they try to see in the try to diagnose chaos not from the point of view of this Lyapunov exponent, but rather from the autocorrelation function. There are several studies are there. So, but in our case, we consider a very large spin so that the classical limit can be taken. So that's why there's a classical limit. So we can find out a classical map for this exact classical map and try to see the thing. And also the quantum sector, we can consider a large spin, like
which means one can think that the quantum fluctuations were small.
Sorry, Subhasis, one clarification. So basically, this is a mapping onto block sphere, right?
Yes, yes.
Sure. But if you are going into the ergodic regime, which means you are having a diagonal density matrix, then which means that the point will not lie on the surface of the sphere; it will be somewhere inside, right?
Yeah, but there is a point is no, it is not true, because it can be completely it will be mixed up. Then only the diagonal density, meaning is a quantum density matrix of a one spin. So if we have a two interacting spin and if we project the one spin density matrix, then it turns out that a z basis it is just diagonal. And if you consider any expectation value of sx, sy, sz, all these things goes to 0 in that sense. So that means it will be completely ergodic. It is completely mixed up in the phase space.
Okay. No, but it will not be idempotent anymore, right? The density matrix on the lying on the sphere means it is.
No, not on the spinning. If we just plot the classical sector, this thing, maybe I'll discuss these things later. I'll just come to this point. So this is basically the consequence. The ergodicity is the mixing in the phase space, and then this quantum projection you can see in the diagonal form of the is a microcanonical.
Yeah, understood. So implication here is it will go all over the block sphere.
Yeah, exactly.
Yeah, I don't think you started your talk yet, right, Subhasis?
Yeah, so that is the problem. So I think I'll just start very quickly. I think I'll just go. So okay, so now the main focus in this talk is there is a quantum scar. So there is these types of states also violate the ETH the eigenstate thermalization hypothesis and gives very anomalous thermalized behavior in the dynamics. So this is actually started the new recent experiment on 2017 done in Harvard with a array of Rydberg atoms on a lattice. So these 51 Rydberg atoms are put in the lattice, and this system is very simple. This is just a localized thing. The atoms are just localized on the site, but only thing is the atom has two states. So one is a ground state and another is a highly excited Rydberg state of that. These are rubidium atoms, etc. So there, if there is a laser tuning is there, then this ground state and the highly excited Rydberg state, they can be connected, they can be tuned by this laser frequency. And this is a simple Hamiltonian. One can just represent it by the sigma x kind of thing. But there is an additional problem which is called the Rydberg blockage of this, like the Coulomb blockage in the quantum dot, etc. So if there is an excitation one site, then it hinders the another excitation its neighboring sites. So there will be no excitations in the neighboring side. If there is a excited state like this black one, then the next neighboring thing will be dark. So this will be white in that way. So there is a projector is necessary to describe this Hamiltonian, and I'll not go into the details of this thing. So this constraint or this projector that makes the system more complicated, the complicated many body system. And it turns out there is a certain initial state. You can take initial state like a density wave type of thing. So one side it is the ground state, next side it is the excited, etc. These types of state. It turns out after a quench, that sudden quench, that this state actually shows a oscillatory behavior. Otherwise, in other arbitrary states, they just relax to the ground state or show the thermalization behavior. Whereas these states that shows a oscillatory behavior. So this phenomena is something very surprising in that sense. And then people analyze this thing, particularly this group of Dima Abanin, even Mikhail Lukin, etc. So they found out a very interesting structure in the Hilbert space. There is a certain emerging symmetry and certain protected states are there which just remains within certain subspace of the full Hilbert space. And so that this revival phenomena can be seen in certain many body system. After that also there are various spin system has been constructed from the like perturbing the integrable structure of certain spin models, and they can show there is some emergent symmetry and some protected states are there which leads to these types of scarring behavior. And this phenomena is attributed to the many body quantum scars and many body quantum scarring behavior. So it's a revival phenomena. Athermal behavior is basically important thing here. But this quantum scars in quantum system has been first identified by Eric Heller in the context of the single particle chaotic system. If one considered the stadium or billiard like system, then the wave function, the nodal structure of the wave function, etc., that shows certain pattern which actually shows the reminiscence of the unstable orbits of this system. So the unstable orbits in the wave function, pattern of the wave function, that is attributed to the quantum scar. So the question arises, what is the connection between the underlying classical dynamics in the many body system and what is the sort of this unstable orbits, how the unstable orbits and this protected state, etc., quantum scarring phenomena are related to this, like a revival phenomena, etc. This is the question. This is not a very direct answer, cannot be given from this many body context, this because there is no such semi-classical limit and one cannot see a very clear picture of these unstable orbits, unlike the single particle system.
So will this description be basis dependent? Sorry, but
it's the eigenstates of this. So this is not the basis dependent. These are the eigenstate local. And okay, so this answer can be found out. We have just understood from some sort of a collective model, which are the promising candidate to connect these two ideas, that revival, athermal behavior, as well as underlying classical unstable orbits. So first model we considered.
Sorry, the question was that
okay,
the eigenstates would look different in different bases, or will they be the same?
No, it's an eigenstate. It's eigenstate. We considered this. This thing was shown by Eric Heller by considering the different eigenstates of this system, and which has a nodal structure of a certain eigenstate, which is the resemblance of these orbits. Okay. So. Well, we considered a simple model which is called the couple top model, and this work was done in with my students. This Deobrata Mondal is a PhD student, Sudip is my PhD student, and this is the reference of this work. So this is a very simple model. We consider two large spins, and yeah.
Here you're going to reverse engineer this phenomena, is it? Is that the idea? Just trying to understand. Is it like you'll
well, we'll see that. We'll see that. Let's see that whether we can
fine.
find out some
fine. Okay.
Yes,
yeah.
Right. So okay. So there is a basically two large spin, and they are interacting ferromagnetically. Basically, it looks like a two spin quantum Ising model. So it is x direction, you can consider like a magnetic field is there, and the z direction is like a Ising interaction, z axis. And the spins are taken to be large in this case, otherwise we don't see much interesting effect, because if we consider spin half, then there is nothing there in that way. So the classical one advantage is that for large spin system, we can take the classical limit and s tending to infinity. So the classical Hamiltonian can be written in this form, where the canonical coordinates are this phi and z is here is cos theta. So theta and phi are the angles which describes the direction of the or orientation of the spin. Sorry, actually, can I request somebody's microphone is on, so it is giving some thing. Can you please switch off this thing? Okay. Okay, so so these are the corresponding classical dynamical equations, and the semi-classical description of these systems of these spins can be found out or described by in terms of the coherent state. So this is coherent state with some classical orientation of the spins. Okay, this is the system. So first we analyze, since we have the semi-classical the classical Hamiltonian classical equation of motion, we can just first thing we can do is that find out the steady state structure and the dynamics of the system. So the steady state structure shows an interesting behavior. The system is very simple, but it shows a various interesting transition. So one thing is, with the increasing coupling strength, ferromagnetic coupling, the system undergoes a quantum phase transition as well as a dynamical phase transition. So quantum phase transition is like the ground state is just bifurcates, it is showing this thing, this is a quantum phase transition, whereas the excited state, the highest energy state, that also shows some sort of an ordering. Here the ground state shows the ferromagnetic ordering, since the interaction between the spin is ferromagnetic, so it's a ferromagnetic ordering is there for ground state. Whereas for dynamical phase transition, dynamical transition, the highest excited state shows an antiferromagnetic ordering. There is certain symmetry one can, I'm not going to the details of this, there is certain symmetry because due to which one can understand, and this is not interesting in this context also, but is interesting phenomenon nevertheless, but not interesting in the context. And so the is basically classical sense, these are like the correspond to the pitchfork bifurcation. And as we know, the pitchfork bifurcation, one symmetry unbroken state that become unstable. So this FP1, this is the fixed point 1 and fixed point 2 that remains as a unstable symmetry unbroken states. And and also there is a interesting another interesting steady state that exists at the zero energy, which is, we call it by FP5, the fixed point 5. So we call it something like a pi state, because this corresponds to a state where like a first spin is aligned to the x-axis and where the another spin is aligned to the negative x-axis, something, or vice versa, so that there is a relative angle between them is pi. So this is the classical orientation corresponding to this state, and this state turns out to be completely unstable state of the steady state. Then we also studied the phase portrait of this system. So before the dynamical phase transition or quantum phase transition, we see the very regular behavior, and there are the 2 points which corresponds to the 2 fixed points like FP1 and FP2, 2 types of fixed points are there. And after this critical coupling mu is equal to 1, this undergoes the transition, and the phase portrait, it shows the 2 different structure, 2 orbits are there. This is corresponding to the quantum phase transition, and the upper one is the dynamic transition. Nevertheless, the important thing is that inside these things, there is some chaotic behavior or irregular orbits are there. So near these fixed points, of course, some sort of regular orbits are there, but the inside there is a irregular behaviors are there, particularly this region and this region. And another interesting thing I can say, that the excitation frequency corresponding to this quantum phase transition or dynamical phase transition, that actually vanishes at this critical coupling, showing that there is a transition. One can also study this quantum mechanically, we have studied. And this system also undergoes another interesting phenomena, which is called the excited state quantum phase transition. I would not like to discuss these things. So this is like the, after the quantum phase transition, if one just change the energy density of the state, it turns out the energy levels, the properties of the energy levels, that changes across the energy density. around this point FP1 and FP2, this unstable symmetry unbroken states, they have this type of transitions, which is called the excited state quantum phase transition. Anyway, then of course, as we have seen from the classical dynamics, there is some sort of chaotic or irregular behavior in between this region. So we studied the system quantum mechanically, closely analyze the system. So we first of all, what one can do to understand the chaotic behavior is the spectral statistics. So we studied the spectral statistics for before the quantum phase transition, when this coupling strength is very small, say 0.5, then we find the integrable regime that the level spacing distribution shows the Poisson type of thing. And after the quantum phase transition in some coupling region, it is an intermediate coupling region, we can see the chaotic behavior. In fact, it's this point I would like to mention, that this model is integrable in both the regimes. So when the if you look at this thing, so when this mu is very small, then of course it is integrable, and when mu is very large, then only this term dominates, and this is also shows the integrable behavior. Only in the intermediate regime it is some chaotic behavior, and after the quantum phase transition, there is these types of GOE type of Wigner-Dyson type of level spacing distribution one can see. But actually this level spacing distribution or spectral statistics can capture only the overall chaotic behavior, but the details of this ergodic behavior can be captured from the properties of the eigenstates, each states. So we calculated the entanglement entropy of the eigenstate at the different coupling strength, and we plotted this with the increasing energy density of these states. It turns out that at central region at E is equal to 0, the entanglement entropy is the largest. It has a peak, and this peak in fact increases, and it saturates in the chaotic regime. It saturates to the maximum possible entanglement entropy. In fact, the maximum possible entanglement entropy one can calculate from a complete random state. In fact, there is a calculation done by Page long back, 91, 92. I think he has done these things for a complete random state. What can be the entanglement entropy of if one bipartition the state and then find out that maximum entanglement entropy of these things. In this case, it is the saturation value, and it turns out that in the chaotic regime, the central band, the states at the band center, that becomes the completely ergodic. However, there are the states which have deviated from this limit. And coming back to the, I think, who asked this question? Probably Bhavtosh asked this question, that how we can find out the ergodic behavior of the system. So there are the various quantities. Now it is also different studies are going on. So we have found out that this measure, the entanglement entropy divided by the maximum entanglement entropy or the relative entanglement entropy, this serve as a basis independent measure of the ergodic behavior. And it turns out that there is a very close connection with a multifractal dimension of the states and this measure. So anyway, so we expect that the central region, the states will be most ergodic states. But we should not forget.
Identified with ergodicity?
Sorry?
So what is the connection between ergodicity and entanglement? Meaning it's, okay, one can define it like that, but...
Yeah, so it is expected that when the entropy, so if you just consider in the classical sense, entropy is basically a measure of mixing. So what is ergodicity? Ergodicity is basically mixing in the phase space. So this will be something that must be related to the mixing in the phase space. There is some connection we have also studied, we have not published yet. So there is certain connection we have found, how the different energy density or one can see this ergodic, classical and quantum sense, the ergodic behavior. So it is related to the mixing property as well as the how it will saturate to the entanglement entropy, etc. There are various measures for this. Okay. Mainly it is related to the mixing in the phase space, you can consider.
Okay.
And quantum sense, how the density matrix become more diagonal. That is the thing. How the diagonal density matrix emerges. that is in the quantum sense. It's correspondence. Okay. So at the central region, the system becomes
Subhasis, so this S1 dot S2 term is responsible essentially when you have two separate large spins, you have towers of this single particles or whatever, this towers of spectrum, right? Eigenstates of the first and the second spin. And what you are doing is you are switching on an interaction term which is S1 dot S2, which is hybridizing them, but probably also you are saying that when it is intermediate, is giving rise to huge level repulsion.
Exactly.
And can we see this?
In fact,
yeah.
So classical sense, it is also very easy to see that in fact we studied, and this picture is not there, I don't present this, but we have studied this thing. But if you consider at energy E is equal to 0, this classical energy, and if you do a classical simulation, you will see that it will cover up the whole phase space. In fact, there is a mixing. In fact, there is a direct question of a direct answer of Bhautos's question, I think. So if you see these states, is a quantum level, and if you consider the same classical energy at E is equal to 0 and start any trajectory from any arbitrary point with the energy density is equal to 0, then you find that it will cover up the full Bloch sphere also. Yes. Okay, in this point, I would like to now remind you one finding from the stability analysis. We found out that there is this FP5 or a pi state at E is equal to 0. There is a steady state. However, this is unstable, but there is a steady state there. So what is the effect of that steady state in the completely ergodic regime? Of course, here we see we can expect the states are ergodic, but what is the manifestation of this steady state? That is the question now. So we construct a semi-classical description of this pi state.
Chiranjeev, could you switch off your mic, please?
And it turns out in this near this energy density at E is equal to 0, if we consider a small window of energy around this energy density E is equal to 0, we find there are certain states having quite a large overlap with this semi-classical state. And this thing actually decreases with the increasing coupling strength. So in some coupling strength above the quantum phase transition 1.1, we see the overlap is quite large. And as we increase the mu, then also this thing decreases. And we try to see this, we identify from this overlap these eigenstates and see their Husserl distribution in the one spin sector. So Husserl, I don't want to discuss the Husserl distribution in details. It is in quantum optics. It is quite well discussed and also related to Sudarshan's P distributions. So this is some sort of a semi-classical distribution or semi-classical phase space distribution of a quantum states. And if we take the semi-classical distribution, then it turns out they have a maximum overlap at certain points, like z is equal to 0 and pi is equal to phi is equal to 0 or phi is equal to pi. This exactly resembles these types of steady state structure, and this is like the scarring. It is not at all completely mixed up and ergodic structure. Whereas if we just increase the coupling strength to 1.7, mu is equal to 1.7, we see that this picture become not really clear, meaning this intensity decreases of these scars. But we also see some type of orbits, the structure of some orbits, but we are seeing this particular steady states intensity that is also decreasing. And we have seen that from our steady state, meaning simple stability analysis, we find that the instability of this steady state is always unstable, and the instability exponent that increases with this coupling constant mu. And somehow this instability, the instability exponent or the Lyapunov exponent of this steady states, Lyapunov instability is directly related to the intensity of the scarring of this system. So as this Lyapunov instability increases of certain steady state or orbits, we find the scarring decreases in that way, the degree of scarring. That's very interesting.
Subhasis, one quick question.
Yes.
In these scar states, again, do you see any idea of an integral of motion in the underlying classical dynamics? Could there be something? I mean, there's an emergent symmetry, and along with that emergent symmetry, could there be an integral of motion, at least in the classical side of the story?
No, actually, we have not found out that this concept of that was another meaning. That was my question, our question, that people generally first started the investigating the scarring phenomena from the integrable, emergent integrable structure, protected state, and all these things. So our point is actually there is a sort of meaning connecting the some sort of a semi-classical steady state structure of the system. So there can be, I think there can be some connection between them, but it is not very obvious that how this will be there. But these are the semi-classical way we have done this.
Okay, thanks.
Okay, so also we found out that we observed these card states do not follow the Berry's conjecture. So Berry's conjecture states that the high energy states of the chaotic system, the amplitude distribution of these states, they follow the Gaussian distribution. So that means if we have a very higher energy states of the chaotic states, and it can be written in this way, the psi i's are like the Gaussian distribution. In fact, in showing the ETH hypothesis in certain system, this conjecture has been used very extensively. So this is some property, that's very interesting thing, and it turns out this is nothing but the eigenstates property of the random matrix system, like a GOE random matrix. They show some type of distribution which is called the Potter-Thomas distribution, but in this case, if you consider the variables which are like mod psi square, then it turns out the distribution is like that, which is nothing but the Gaussian structure of the psi I basically. So this distribution is the Potter-Thomas distribution, and if we compare with the Potter-Thomas distribution, we see there is a very much deviation of this distribution of these card states. But as we increase the mu, then this will go close to the Potter-Thomas distribution, which is attributed to the decreasing degree of scarring in the system. Okay, and there's another type of scar also we have found out. And yes, coming back to the Siddharth's question, now there is some sort of a symmetry consideration is there, but not it is exactly a symmetry, but I would say that is a solution of the exact dynamical equation. If we consider the actually okay, I'll tell it in the details. So the region we considered is the energy density E is equal to 0. We found out that entanglement entropy saturates almost all the states, and it cannot show much difference in that. I mean, all the states behave in the same way. But if we calculate the Shannon entropy, then we find a very interesting structure in this regime, which is not shown in the entanglement entropy. And Shannon entropy, most of the states actually follow a band-like through a band-like structure around the maximum value of the Shannon entropy, which is obtained from the random matrix prediction. And there are few states which are deviated from this. And if we try to analyze those deviated states from this maximum limit, then that reveals the different type of scar. The scars of some orbits are there. And we find out that there are some orbits can be constructed under this type of constraint. If one considered these types of constraint, these are not really constraint. From the equation of motion, one can show this turns out to be a steady state. And then one can solve the another degree of motion, and these degrees of motion actually is a very simple equation. These are the equation of an effective Lipkin-Meshkov-Glick model, which is an integrable model, and one can get the one can obtain the solution of the periodic orbit analytically in terms of the sinc function or etc. So within these classes, one can obtain these types of periodic orbits with different energies. And it turns out these periodic orbits are nothing but they are actually under this constraint, they form this periodic orbit, stable orbit. But if one just slightly violate these conditions, this constraint, then immediately they become unstable. One can also find out the instability of this from the monodromy matrix, Lupinov instability, and we found out that they are actually unstable, but only exactly under this constraint they become stable periodic orbits, and this is the manifestation of these things. So these two types of symmetry classes, they get mixed up in these card states. And also they violate the Berry's conjecture and deviates from the Potter-Thomas distribution, all these things that happen here. And the dynamical signature, finally, the dynamical signature of the scarred state that we have also found out from the survival probability. That's interesting thing is that if we start with a state and find its overlap with a time evolved state psi t and how it behaves, that we can find out the non-ergodic behavior. So ergodic behavior, it predicts that after a long time it will go to the GOE limit, which is given by 3 by n. This is the prediction for the ergodic structure. And for non-ergodic behavior, there can be deviation. So we find that the for scar states, like the first type of scar, which correspond to some steady states, there we find there is a sort of aperiodic, it's not a periodic revival, but very much like a revival phenomena is observed for the short time regime. Whereas if one start with the same energy density at E is equal to 0, some arbitrary coherent state, they just decay very rapidly. And for long time, we see that there is also deviation from this GOE limit, the random matrix prediction. And moreover, the final time evolution of the state that retains this scar also. Whereas for any other coherent state, this becomes a mixed up type of a thermal state after time evolution. And then for the another periodic, the eigenstate which contains the periodic orbit type of scar. So for those states, we have calculated this out of time ordered correlated. This is something that is proposed very recently to quantify the Lyapunov exponent in the quantum system, but we are not using this thing or Lyapunov exponent or etc. We just want to see the qualitative behavior, the change of this behavior of a ergodic on an arbitrary state and the scarred state of this. So this quantity is called the out of time ordered correlator, and these operators we have chosen a spin operator, some S1Z by S, and two types of density matrix we constructed. First one is a microcanonical density matrix, which is constructed within that energy region, meaning a small window of energy around E is equal to 0, which have the random or the maximum Shannon entropy, those types of state. And we find out there is a behavior like that. This red color is the ergodic for the ergodic density matrix, microcanonical density matrix. This is the out of time ordered correlator shows, and there is a saturation. In fact, in our previous studies, we have found out it is not the Lyapunov, it can only capture the Lyapunov exponent. This is not only the idea, but for most of the quantum many-body systems, if it is ergodic or some sort of an delocalization phenomena, etc., these things can be understood from the saturation value of this. So saturation value is a very important criteria for the ergodic behavior, not this growth rate. Of course, the growth rate is quite fast, but not always one can get the quantify the degree of chaoticity from the growth rate, but the saturation is also a very important phenomenon. So here it is a saturating, whereas for the scarred state we see there is a oscillatory behavior. And interestingly, this period between these maximas, this correspond to the period of the unstable orbit of these scars. This is quite surprising, quite interesting in this thing. So this is the dynamical signature of these scars. And next work I considered, we considered a Bose-Josephson junction. So Bose-Josephson junction is created by a double well trap and loading the condensate in the double well trap so that they can be considered as two these superconductors in contact, and there can be the phase difference and number difference. They are the conjugate variable and they oscillate also. This oscillation has been observed in experiments in Heidelberg group of Oberthaler's group, as well as this work of Subodh Senoy and CISA group. They have analyzed the various different modes of this or oscillations of this Josephson junction. It turns out due to the nonlinear interaction, there are two types of modes are there. One is a pi oscillation mode, and there is a self-trapped mode. So self-trapped mode was a main focus of these types of experimental studies, where one trap contains more number of particles. These types of steady state is a self-trapped state. And there's a pi oscillation, is that the relative phase between these two condensates in the two wells, that is become pi. and they will oscillate around this pi. This is called the pi oscillation. So for our study, we focus on this pi oscillation state and see how it behaves.
Subhashish?
Yes.
Hello, Subhashish. So one is one in which the phase is fixed, your numbers are not fixed, I guess, and in which the numbers are, you are
Both the
saying almost.
cases, yeah, both the
Yeah, so
cases,
just
phase and number are conjugate variable, but I'm just considering, if I consider a steady state corresponding to
right.
these oscillations, so
Yeah.
this will be a steady state where the phase difference is, I think phase difference will be also be pi here, and there's a number difference. Main thing is the number difference. Whereas in this case, the number difference is 0, but the phase difference will be pi. And normal
But
branch of the
can
AC
you
Joseph.
hold on to a fixed phase difference and number difference simultaneously? Or when you say that, let's say the phase difference is exact, then the number difference must be an expectation value, right? Which you are saying it is fluctuating in principle.
So phase will be fluctuating and the number is also fluctuating. So from the number fluctuation, only one can see these types of oscillation experimentally. So of course one cannot see this like a completely localized of this phase, etc.
Right. So that's what I'm trying to understand. What is the limit?
There is a phase diffusion, a little bit of these things, but it is something related.
Okay, so the phase is almost locked. The number is not that locked. That's the situation.
Yeah.
Okay, fine.
Okay, so actually this is the work we started. Sudeep started this work in his BSMS project. So we are interested to study what happens in presence of, when in these types of modes, in presence of dissipation. So we connect this Bose-Josephson junction with some bosonic bath, and so that the phonon modes of these bosonic baths that will be coupled to this oscillation. And one can write down this system is a Bose-Josephson junction and a bath type of thing, phononic bath, and this work is published here, but this is not the main focus. So the bath meaning it consists of lot of frequency, phonons of lot of frequency, but we are now mainly interested when the Bose-Josephson junction is coupled to only one mode. This can be achieved by putting this Bose-Josephson junction into a cavity mode, for example, so that there is only one frequency is there, and we can just forget about the cavity loss and etc. Just a mode interacting with the Bose-Josephson junction. That is the main focus. And this model is described by this. This is again one can write down in terms of the spin language. I'm not going into details. It's just a creation annihilation operators of the bosons in the two different traps can be ultimately written in terms of the spin language of a large spin, so that S is equal to n by 2 number of bosons, and this Sx term represents the oscillation between two modes, and this Sz square is the charging term, and this is the coupling with the mode, and this is the frequency. Omega 0 is the frequency of the mode, external mode. In fact, we'll see in our study this omega 0 plays a very important role, and this is the work done with Sudeep. And so this is the classical, again we can have this classical description of this system in terms of the coherent state. We can get the classical equation of motion, and it main important thing is it also undergoes a quantum phase transition above certain critical coupling. Coupling here is the coupling between the bosonic mode and the Bose-Josephson junction, and above this critical coupling it undergoes a phase transition where one trap contains a more number of atoms, which is like a self-trapped situation here. So we again we follow the same type of prescription. We calculate the entanglement entropy of these different states, and with the increasing coupling constant, it gives the overall ergodic behavior of the system. We see that the system after the quantum phase transition, this line is a quantum phase transition when there is a kink in the ground state occurs, and above the quantum phase transition we see the red region becomes sort of weakly ergodic. We call it a weakly ergodic because the relative entanglement entropy does not really saturate to the value of 1, but it is still less than 1, but it is increasing with the increasing energy density. So it's a sort of weakly ergodic regime we get, and these things are the non-ergodic or type of behavior one can see. And there's a controversial thing whether there is a sort of crossover from non-ergodic to ergodic behavior one can see across this energy density or not. But there is an important thing is that there are the steady state structure. One steady state is at EC, which is the corresponding to the symmetry breaking. So it's a symmetry unbroken, unstable state is there at EC. And there is another state which is E0, which is corresponding to the pi oscillation, what I just now described. So this pi oscillation state can be there at this energy density E is equal to 1, and which can be extended in the weakly ergodic regime. Moreover, this pi oscillation, this is like this one EC, that is a completely unstable thing, because after pitchfork bifurcation, we know the symmetry unbroken sector state becomes completely unstable. But here pi oscillation state can become stable up to certain point above the quantum phase transition by tuning the frequency of the bosonic mode. That is a very interesting feature in this problem, in this model. And then it can be unstable, this pi oscillation. So we again try to see the manifestation of the pi oscillation. We see the same type of whatever the spectral statistics it shows also from the classical dynamics. We also find out that after quantum phase transition, system becomes sort of shows a chaotic behavior, although there is a quantum phase transition and there's a stable pi oscillation, but still this become large region become chaotic, and the manifestation of this chaos can be seen from the level spacing distribution from Poinsot to GOE, as well as there's another feature that's the R average is called this is a ratio of consecutive level spacing. It shows a crossover from Poinsot to GOE like structure, onset of chaos is seen. And we have also seen there is a very strong effect of this pi oscillation, stable pi oscillation. If we consider a region after quantum phase transition, some fixed coupling, and we tune the frequency of the bosonic mode, then this pi oscillation can become from stable to unstable. And if it's become unstable, then the Poincare section at this particular energy density, it shows these types of behavior, which is chaotic in this case, is a classical state. And when it's become stable, then it shows this mixed phase structure. And this is the regular orbits around the pi oscillation. So this mixed phase behavior in the classical thing is the very important thing for the both for the non-ergodic behavior as well as for the quantum scarring phenomena, it turns out. And if we calculate the entanglement entropy and see that when this is stable, this pi oscillation, then at this point when the pi energy of the pi oscillation, we see there's a dip in the entanglement entropy, whereas when the pi oscillation is unstable, we see the increasing, just a monotonic increasing structure of the entanglement entropy. It is also shown from the R average, which quantify the degree of chaoticity. So it is decreasing from the in the unstable pi mode, it is reaching the GOE limit, and then when the pi mode becomes stable with the increasing frequency of the bosonic mode, then the chaoticity actually reduces in this case. Also the dip in the entanglement entropy that shows the similar behavior. So this was a strong effect of the how this a classical stable fixed point influence the quantum ergodic behavior in the quantum system. There is a strong evidence of that. And we again found out
evidence of phase transition, also the fact that there's this dip in this, meaning this kind of intruder which you have in the
No, it's nothing to do with the phase transition. All these things are basically when there is a onset of chaos, etc. This happens in the smooth way. These are the crossover phenomena. There is no such.
But points is in microcanonical thermodynamics, one sort of when you have this kind of a funny shape of S versus E, that is one way to sort of characterize the phase transition, or?
I don't know these things. Okay. This is an entanglement entropy, by the way. It's a reduced system, not the total entropy. Okay. And so again, we can study the effect of this pi oscillation in this system, and we find out the semi-classical description of the pi mode is written in that way in terms of the coherent state. We also see from the Husserl distribution, it has a strong scar-like behavior. and there are if we just resolve the Shannon entropy part, then we see there are the deviated state, there are few deviated state, and there is a band like structure. However, as I mentioned, this is a weakly ergodic regime. E is equal to 1, where there is a where at the energy density where you are considering this pi oscillation, there it is not completely ergodic. This is still weakly ergodic, so it is less than the maximum limit or the limit of the random matrix prediction. And if we consider these types of deviated state, we see there is a either there's a scar of the fixed point, or we see the periodic orbit corresponding to the pi oscillation. However, the pi oscillation is unstable in this region. We have considered the region when this is unstable, but we see the very clear signature of this scar. And this effect of scarring is also seen from the overlap function, but we find this overlap also decreases with the increasing the coupling strength, as well as the deviation of the Shannon entropy. These states are deviated from the band of the Shannon entropy, and if we increase the coupling strength, we find the number of states will decrease here, the deviated state, and they will merge to this band.
I think he lost his connection.
Looks like that.
This band will be more deeper. Sorry, hello, can you hear me now?
Yes.
Sorry, we lost you for a while. Again lost.
Yeah, now he seems to have gone.
Yeah, he has. I think he has two this thing on. One is presenting from two different one computer, one phone probably, because he is still logged in one. He has been logged out in now. Now he left completely in both the devices.
He's probably trying to restart. Yeah.
Right. Now he told me that he even during when he takes classes, he has problem with connection.
To make a bad pun, he was localized here, but now he thermalized.
Right, he's back.
Yeah, sorry, this is
So while you are loading your presentation, maybe just a suggestion, why don't you take a broadband connection at home? That would be better than the mobile thing.
yeah, I was thinking that thing, but yeah, after this thing, this pandemic thing, there's a delay in all this process. Yeah, is it visible now? Hello?
Yes, yes.
Okay, so basically it's a similar type of analysis we have seen. Only thing is that we have plotted the degree of, we have just quantified the degree of scarring from this overlap function, as well as the deviation of this Shannon entropy part of this. And so it turns out that with the increasing coupling constant, this degree of scarring in terms of this deviation of the Shannon entropy, that decreases, as well as the overlap function, that is also decreases. And as I mentioned before, this is truly related to the fact that it is a instability, Lyapunov instability of this particular fixed point. In fact, Lyapunov instability increases with this coupling strength, and the scarring also vanishes in that way. So it is very much a delicate issue to finding out this types of scar region. So it is at the when the it is just become unstable, some steady state or some orbits, then within that region where it is a mixed phase space behavior is there, this is the ideal regime to find out the scar or the effect of scarring. Okay. Now, the dynamics of this scar, it shows a very interesting effect that as I mentioned previously, that there is a survival probability as usual show these types of aperiodic oscillation, but the revival phenomena as well as the long time behavior of the survival probability shows the deviation from the random matrix prediction. But there is an interesting quantity which is actually showing us from the very beginning that he was very much not very comfortable with this idea of the phase difference. Yes, there is a phase fluctuation always, and we can write down in the many body sense there is a phase operator, of course, and try to find out what is the distribution of this phase and whether there is a phase diffusion. So if it is a completely thermal and ergodic regime, then what we expect, the phase diffusion will completely destroy the sort of Josephson oscillation between them, because there is no such well-defined phase between these things will be there. So this quantity cos phi average, this is the sort of quantum mechanical average in terms of these phase states. If we calculate this quantity cos phi, then we expect for the ergodic states, which is shown in terms of the red line, it is going to 0, because the phase distribution become a flat distribution, so that cos phi average just vanishes. This is a characteristic of the phase diffusion for the thermal noise or etc. Whereas if we start with this pi state, however it is unstable, then if it turns out that after the long time evolution, it still has some value and it is close to the negative direction. So in ideally, if there is a pi oscillation, then cos phi should be -1, but it's not exactly -1, but something, some negative value which is there, not going to 0. There's a strong signature or strong difference between the scarred state and the excited state, and then the time evolution, this can be observed in that way. So this is an experimental setup. In fact, previously people have this Oberthaler's group in Heidelberg. They have calculated this phase diffusion in the thermal bath, or in presence of the Bose-Josephson junction, in presence of some thermal cloud, etc. So these are due to the thermal decoherence. This phase diffusion goes in that way. So we believe that these types of experiment can be done to understand this type of scarring. And also, while we have just submitted the paper and fighting with our referees, etc., that time we found there's another paper came out that is the the Rydberg atom was considered. Hello, can you hear me?
We lost you for a bit. Now we can hear you again.
Okay, so this is just a scarring of the Rydberg. Sorry, the hello.
It's fine. Yeah, fine. Subhasis?
I think Subhasis is gone.
Yeah.
Sorry, yeah, can you hear me now?
Yeah,
Yes,
we
now
can
we
hear
can
you
hear
now.
you.
Okay, just 1 minute. Just give me a minute. I just change this connection. 1 minute.
Bhator,
Yeah, I don't know.
Nearly 1:30.
Yeah, I think he needs another 5 minutes or so. So I thought, yeah.
Okay, so sorry, this.
Subhashish?
Okay. Can
Now it's completely gone, I suppose.
Sorry, hello, can you hear me?
Yeah, we can hear you well now.
Okay, so sorry, it was just a so bad luck. So I just changed the connection and immediately that new connection of this VI. So now this VI that has gone to something. So this is the condition of our whatever. Anyway, so this is just the last part. So there's a new experiment has been done where there is a scarring in the dipolar gas has been observed. So this is somewhat in the similar line where they have found out that some many body state can remain stable in the unstable branch, and they are calling this thing as a signature of the scarring in this system. Okay. And there's a very I think all these things can be summarized very nicely in the one picture. It is made by Devobroto and also by Sudeep. So thanks to them. So the whole thing can be summarized in this picture. So the first column that shows, so forget about the system is quite different. So we are studying some driven system in that case. But important thing is that if we consider the first column, this shows the classical phase space behavior, and forget the second column, but the third column shows the survival probability, and last column shows the entanglement entropy. So what they have done, they have considered a particular region in the phase space, constructed a coherent state, and then did the time evolution, quantum evolution, full quantum mechanical calculation, quantum evolution for long time, and then calculated the survival probability as well as the entanglement entropy of the system. And is very clear that whole information of the classical phase space, particularly the region which at the stable region or the fixed point, that is captured in the survival probability and the entanglement entropy. Though the region where there is a fixed point structure is there, there is a maximum, the survival probability is large, so it's a much deviation from the GOE limit will be observed in this region. So these are the consequence of the thermal behavior. And also the other way happen in the entanglement entropy. So this region, the entanglement entropy is less, whereas the ergodic regime, this is red color, all this. So the structure of the phase space somehow is there in the in the survival probability as well as the entanglement entropy. So the local behavior of the classical phase space is somewhat there. So this is the main conclusion of my talk. So this is a way maybe one can think of the scarring, that there may be the sort of mixed phase space behavior in the many body system. One can need to understand or try to find out the collective dynamics which gives rise to such a fixed point, maybe the higher energy state. We are always focusing on the ground state, but ground state is no good in this case, only the higher energy states, and there one can see the various athermal behavior and deviation from ergodicity. So this is a conclusion. Same way, so we are now studying some sort of driven system, the scarring in the driven system, like driven couple top model, and there is also some preliminary investigation shows that there is also scar, but scar of some type of period 2 type of things, that is a 2 cycle type of systems. Okay, so I'll just stop here. So these are the main conclusion.
Okay, so thank you, Subhasis. I think what we can do is that we can formally close now, but the discussion can go on.
Okay.
Yeah, please go ahead with questions. Yeah.
Okay, Subhasis, tell you here. Can I ask one question? Okay, there are not many people.
Yeah, sure.
It was more of a, I mean, this is something which needs to be discussed once we meet, I think. But look, the one comment you mentioned in about our when answer was when you asked that large entropy and more, ergodicity. So you mentioned that there is more mixing in the phase space. Now, so that
in the previous picture,
Right,
this picture you are considering, yeah.
No.
So these are the
Yeah, no, I'm not talking about a picture. I mean, let's forget the picture. Now, there was another kind of. Anyway, so that definition actually I found a little counterintuitive, because you see, generally large entanglement means the system is more ordered. For instance, if you take a antiferrometric Heisenberg model, so the entanglement is highest at the lowest temperature where you have maximum sort of order, and of course there will be underlying thermal fluctuation. So when we go to the classical picture, the understanding of when you have a phase space picture, let's say you divide them into cell, like Heisenberg cell, PQ, and if the system is in 1, then the entropy is 0. If the system basically expands into
no, we are not doing in that way, that 1 0 in that way, but what we are doing is the following, that it's a zero temperature calculation first of all. So the point is that how the local behavior of the classical behavior will reflected in the entanglement entropy. So we can, or the time evolution, particularly the time evolution after time evolution. So if we just take a certain region, a small region in the phase space, and find out the classical variable of this phase space and construct a quantum state, that is semiclassical state, and time evolve that semiclassical state, and we can get the entanglement entropy or survival probability of this, and we are plotting. So we find out if it is corresponding to the regular region of the phase space, the entanglement entropy is less, whereas if it goes to the sort of chaotic region in the mixed phase space structure, if it goes to the chaotic region, then it will be high. Like in this picture, if you see, this is a highly mixed phase space. So these are the sort of fixed points are there in this case, and inside there's a complete mixing is there. So the mixing is reflected with the large entanglement entropy of this red color, whereas the fixed point regions that will have the lower entanglement entropy. This is the correspondence I'm saying.
So it's the other way around. You're building from local states, right?
Yes, the local state. Yeah, exactly.
And if you have a equal contribution from all the local states, then you will get the maximum entropy.
Yeah, then there can be something. There can be just averaging out all this. That is a possibility. Yeah.
So, any other questions or comments?
We are completely out of time, right, Bhavtosh?
Yeah, actually, I am responsible for that.
No,
it's for this. There's some problem happening. In fact, I thought that I'll.
Anyway, so I think people want to discuss. We can discuss another couple of hours.
Yeah. I think that should be fine. I'm going. I'm off to lunch.
Okay.
Okay, bye.
Shall I stop recording, or you want to keep the recording on? Maybe I can stop recording. Huh?
You can stop.
No, I think recording, you can stop these things recording.
Yeah,
Okay.
yeah.